Welcome you once again to my channel of physical chemistry. Today we are going to discuss the next part of the electrochemistry, that is we are going to discuss once again in the brief the conductance, and then we are going to discuss in brief in detail about the Ostwalds dilution law, right? Now, as explained you earlier also, the Arrhenius theory's first postulate is that the electrolyte when dissolved in water or the aqueous medium, it gets dissociated into its respective ions. Now, what does mean by the electrolyte? All of we know that the electrolytes are those chemical compounds which can conduct the electricity. Now, what are these? These are the acids, bases or their salts. Now, when these, according to Arrhenius theory, when these gets dissolved into water, they gets dissociated or ionized into their respective ions, as a result of which the electrons gets freed out, and these electrons are responsible for conducting the electricity, right? Now, the electrolytes, as earlier also I have explained you that they are of two types, right? The strong electrolytes and the weak electrolytes. According to Arrhenius theory, the strong electrolytes are those electrolytes which when dissolved into water immediately gets ionized to a maximum extent. Not 100% at all, but the maximum number of ions gets formed and electrons get freed out due to the dissociation immediately after dissolving the strong electrolyte into water, right? Next is the weak electrolytes. These weak electrolytes, they get, when they are dissolved into the water, their ionization take place, but to a very lesser extent or to a poorer extent. So, according to Arrhenius theory, weak electrolytes are those electrolytes which when dissolved in water gets ionized, but to a very poor or lesser extent, right? Now, one thing I would like to tell you, dear friends, over here, that among all the acids, whatever acids you know that are available with us in this universe, only 3 acids are there that are the strong electrolytes. What are these strong electrolytes? Among the acids are the hydrochloric acid, nitric acid and the sulfuric acid. See, that is only these 3 acids are the strong acids, right? All other acids, whatever that exist in this nature, whatever that are being synthesized in the laboratory, all are weak acids, mind well. So, only 3 acids strong behave as the strong acids or the strong electrolytes, that is the hydrochloric acid, the sulfuric acid and the nitric acid. Clear? So, among the acids, the weak acids, examples of the weak acids can be given as all organic acids, that is oxalic acid, formic acid, methanoic acid, butyric acid, propanoic acid, all the other acids, succinic acid, phthalic acid, all the other acids, all the organic acids and other acids than these 3, that is sulfuric acid, hydrochloric acid and the nitric acid, all organic acids are the weak acids, right? Similar to that, we come to the bases also, that is the alkalis or the bases. The strong bases only are 2. In whatever that exists in this nature, only 2 bases are strong bases. What are these? Sodium hydroxide and potassium hydroxide. All other bases, that is all other hydroxides other than these 2 are the weak bases, right? So, I have given you the examples of strong acids, strong bases, weak acids and weak bases. I hope all of you will keep this in mind very well. And the salts that are prepared from these strong acids and strong bases, that is for example HCl plus NaOH, when they are when they are reacted with each other, we get the NaCl and H2O, sodium chloride and water. So sodium chloride will be the salt of strong acid HCl and strong base NaOH, right? So likewise, the salts which are prepared from strong acid and strong bases are called as the salts of strong acid, strong bases, and they also behave as the strong electrolytes, right? On the other hand, the salts prepared from weak acids and weak bases are obviously these weak electrolytes, right? Now, if the acid is a strong acid, so the base is a weak base, and the salt prepared by them, they also behave as the strong electrolytes, right? But ionization will improve, but not to the maximum, right? So I have given you the examples of the strong electrolytes, strong bases, and their salts also, right? Now we will come to conductance again. As and then I am telling you that the conductance is nothing but the continuous spontaneous flow of electrons when the electrolytes are dissolved in water, right? Now and the electrolyte is connected with the electricity. Now we can come to the Ohm's law. What does this Ohm's law say? Ohm's law says that the current in amperes is equal to the voltage, that is the electricity supplied, and the resistance that has been to be phased by the electrolyte, right? When considered this, then it is said by Ohm's law that the current in amperes is directly proportional to the electrode potential or the potential difference that is being developed in between the electrodes in the cell, right? And it is inversely proportional to the resistance, right? When the electrons flow from one electrode to another and it forms a circuit in the electrochemical cell, they have to face some resistance also, and that is why the resistance is also to be considered. And it is found out that the resistance is inversely proportional to concentration. Resistance is inversely proportional to conductance, that is C. So we can also say R is equal to 1 upon C or 1 upon C is equal to R. Clear? So there is the inverse relationship between the resistance and conductance. Conductivity is inversely proportional to resistivity. Clear? But resistance is there, right? Now there are different reasons or factors that are responsible for creating this resistance. We can say that the resistance may cause due to the cross-sectional area of the metal rods. It may due to the presence, it may the factor may be due to the concentration of the conducting solution, right? As well as it also due to the current supplied externally to the circuit. Clear? So the Ohm's law says that I is equal to, mathematically it can be explained as or equated as I is equal to E upon R, right? Now the Ohm's law, as the Ohm's has proposed it by its name, so the conductance, so the resistance have its units as ohms only, right? As the conductance is inverse of resistance, obviously the conductance has inverse of ohms, that is the unit of conductance is inverse of ohms, and we can simply reverse it, that is MHOS, mhos. Ohms is OHM, ohm, while conductance is, unit of conductance is mhos, MHOS, right? So likewise the conductance possesses the unit of mhos. Clear to everyone? Now in brief we will just discuss about the definition of the specific conductance, equivalent conductance and molar conductance. Dear friends, as I have told you that the cell is comprised of the two half cell. one electrochemical cell which acts as a device to generate the electricity or to utilize the electricity to generate the chemical energy, right? This electrochemical cell is made up of two half cells, that is two portions we can say, and one portion is supposed to be one half cell and another portion is supposed to be another half cell. These two portions, they are connected internally as well as externally through the metallic rods, right? Internally through the salt bridge and externally with the metallic wire. Now the one portion is, that is one half cell, is composed of the metal rod which is dipped in the aqueous solution or any conducting solution or its own salt solution. For example, zinc when dipped in the zinc sulfate solution, it forms one half cell. Copper when dipped in its own conducting solution, let us say copper sulfate, it forms another half cell. When these two half cells, they are connected externally through the metallic wire and internally through the salt bridge, that is the specially made for the internal connection, through which the ions can flow from one part to another, one half cell to another. It forms one whole electrochemical cell. Clear? Now as I have told you that the conducting solutions concentration may cause some resistance, right? So it directly also contribute to the conductance, right? So the specific conductance can be defined as the conductance which is developed by the two half cells when they are kept 1 centimeter apart and their cross-sectional area is 1 centimeter square, right? So specific conductance can be defined as the conductance that is generated by the electrochemical cell when the conducting solution, two half cells are kept 1 centimeter apart and the cross-sectional area of the metal rods is 1 centimeter square. Clear to everyone? Then we come to the equivalent conductance. We can say that the equivalent conductance is the conductance generated by an electrochemical cell when the concentration of the conducting electrolytic solution is 1 gram equivalent. The concentration of the conducting solution is 1 gram equivalent. So once again I will define the equivalent conductance as, the equivalent conductance is defined as the conductance that is developed by an electrochemical cell when the concentration of the conducting solution is equal to 1 gram equivalent, right? Next is the molar conductivity. Molar conductivity is defined as the conductance developed by the electrochemical cell when the concentration of the conducting solution or the electrolytic solution is kept to be 1 molar. Clear to everyone? Now the specific conductance is denoted by kappa, or we can say it is denoted by small k, right? The equivalent conductance, it is denoted by lambda, while the molar conductance, it is denoted by mu, right? So we have seen all the conductances, specific conductance, how it is developed, how the equivalent conductance gets developed, and how the molar conductance gets developed by an electrochemical cell, right? Dear friends, this conducting solution, that is the electrolytic solution, plays an important role in the conductivity. The concentration of the conducting solution plays again more important role. As we go on diluting this electrolytic solution or the conducting solution, the formation of ions or the number of ions formed gets increased. It reaches to a limiting value, right? So what is the effect of dilution on the electrolytes? That are going to discuss in my next video. Now we will discuss the Ostwalds dilution law. So on the basis of that only, the Ostwalds dilution law is proposed by the scientist Ostwald, and it has given the direct relationship between the degree of dissociation and the concentration, right? So the relationship that is being given by the Ostwald is between the degree of dissociation and the concentration of dilution, obviously. Now dear friends, the degree of dissociation, once again I'll revise. What is degree of dissociation? It is the ratio of the total number of dissociated molecules divided by the total number of undissociated molecules, right? When the electrolyte is dissolved in water, initially there is no ionization. So at the initial state, the ions, the concentration of the ions is obviously 0, right? As the electrolyte is dissolved in water, after some time, let us say after a minute or so, the ionization has begun, and it will reach up to a equilibrium state, and then there will be equilibrium between the total number of dissociated molecules as well as total number of undissociated molecules, right? Now let us suppose that if HA is a weak acid, yes dear students, the Ostwald's dilution law is applied only and only for weak electrolytes, because it is difficult to find out the concentration of weak electrolytes, right? The degree of dissociation of our weak electrolytes as their ionization is poorer or to a lesser extent, right? So if we consider HA is a general formula of any weak acid, HA, it will dissociate into, let us say, when dissolved into the aqueous medium, it will dissociate into H positive ion and A negative ion. Clear? Now the general equation at the equilibrium can be represented as HA when dissolved in water H2O. HA plus H2O will give H positive ion plus A negative ion. H positive ion will be there in the aqueous medium, as well as the A negative ion will be there in the solution form or aqueous solution form, right? Now, as I told you just now, that initial concentration of HA will be, there will be only and only HA, that is undissociated molecules only, before the ionization starts, right? HA will be initially present, that after some time the ionization will begin as H positive and A negative. Let us suppose that if capital V is the volume of water, then the 1 by V will be the initial concentration, then after equilibrium it will be alpha upon V. Alpha is the degree of dissociation, and the alpha upon V concentration will be initial concentration of A negative ion and H positive ion, right? That is in the aqueous medium. Then at equilibrium, at this stage, when there is equal number of undissociated and dissociated molecules present in the aqueous medium, at equilibrium, the concentration of these ions as well as the undissociated molecules can be given as 1 minus alpha upon V and alpha upon V respective for the H positive and A negative ions and the HA molecules, right? So if Ka is the equilibrium constant of acid, dear friends, equilibrium constant for acids is represented by Ka, that for bases is represented by Kb, that all you know. So Ka will be equal to, by applying the law of mass action, we get molar concentration or the active concentration of H positive ion multiplied by the molar concentration of the negative ions divided by the molar concentration of the undissociated Ha molecules. So we can substitute the values of the concentrations at the equilibrium as alpha upon V multiplied by alpha upon V divided by alpha 1 minus alpha upon V, right? Why 1 minus alpha upon V? 1 is considered to be the total number of undissociated molecules, and out of that only alpha has been subtracted, alpha has been given out, right? So Ka is equal to the alpha square upon 1 minus V into 1 upon V. By solving this, we will get the alpha upon V into alpha upon V into alpha upon V divided by 1 minus alpha divided by 1 minus alpha upon V. This we get as Ka is equal to alpha square upon 1 minus alpha square upon 1 minus alpha into 1 upon V. But 1 upon V is what? V is what? V is the volume of water in moles, right? It is the, we say in liters, it is, V is the volume of the water taken for preparing the solution in liters, right? So 1 upon V is equal to C, that all we know. So 1 upon V can be replaced by C, and we get Ka is equal to alpha square into C upon 1 minus alpha. But dear friends, 1 minus alpha, as the electrolyte is a weak electrolyte and its dissociation does not take place to a larger extent. It dissociates into its ions to a very poorer extent. So 1 minus alpha is very negligible, and it can be taken as good as equal to 1. So 1 minus alpha can be replaced by 1. So we get the equation Ka is equal to alpha square into C. Ka is equal to alpha square into C. This equation is given by Ostwalds dilution law, and according to this equation, the law has been proposed by the Ostwalds that the equilibrium constant of any weak acid or any weak base is directly proportional to its degree of dissociation, right? And the concentration of the electrolyte dissolved in water. So the Ostwalds dilution law has proposed that there is direct relationship between degree of dissociation and concentration with that of the equilibrium constant for the weak acids, or the weak bases. In general, we say it is for weak electrolyte. I think you must have understood the Ostwalds dilution law as well as the conductance concepts, basic concepts of the conductivity. I hope you must have liked this video. Don't forget to share and comment, my dear friends.